So let's go ahead and pull up some basic models. Cool. So this is going to be a little bit of review stuff. So if there's any questions kind of going forward as I go through, just kind of stop me and ask them. But we'll kind of, I don't know, I see it's already been run before, so I want to make sure we do this from scratch. So our first model is going to be our white noise model. So our white noise model basically is just saying a stationary series, essentially it's random noise. So one thing to note is that it's going to have a fixed constant mean. Basically, the mean's not going to change. Usually we can set that to 0 to make it like nice and easy. If it was something else, basically the whole white noise model would just be bumped up by some. It has a fixed constant variance. Basically, there's no dependence in time. There's no correlation over time. So the pattern is random. Note that like when we say like Gaussian white noise, our Gaussian is a mean of 0, variance of 1. So standardized and everything like that. Okay. So just to kind of look what this looks like, right? I'm just going to create some random data here. So 100 days, our average temperature will be 10. So this will be our mean and our standard deviation of 3. And basically create a normal distribution off of this. And if we actually plot this out, so remember it's going to be like starting from January 1st, 2015, going 1st, 2nd, 3rd, 4th, all the way for 100 days, and just plotting out what that temperature looks like. You can see we basically have this randomness going on here. So you can see is that there's no direct pattern in here. Like you can maybe try to find a pattern here, but it's really just random noise. And note that also because it's random noise, these points right here are not even dependent on the previous point. So if I get like 14 or 15 here, the next day has the same distribution as any other day. And if you imagine where the average is, you can see it's about 10. Okay, cool. Make sense so far? All right, awesome. This is where like basically we want something that's like white noise to start off with. So it's nice to know how we can generate this. Our next part is a random walk. So this is kind of like, we'll see the next few models that we kind of increase by. Essentially, we're just modifying our white noise model. So our random walk model basically is that we have the same idea here. There's no specified mean, there's no specified variance, but there's a strong dependence of time. So over here, there was no dependence of time at all, where the next value coming up doesn't depend on the previous one. So it's basically just randomly going up and down. But a random walk starts somewhere and then can go either left or right and says, all right, let me go left, let me go right. Okay, I'm gonna go left, and it goes left. So you can see that basically if you start with a very high value here, it's likely, even though it's random, it's likely to be it's not going to be all the way down here likely. It's likely going to be near this point over here. Does that make sense? Okay, so that's where basically this formula comes in, where this YT basically saying, okay, what's the next point going to look like? Well, you take the previous point plus epsilon t, which is epsilon t in this case, is just going to represent our white noise model. So this is basically saying, hey, just take some white noise. So we say, we're at this point and say, all right, you take the previous point, which is this point, and say, give it a little bit of white noise, essentially, like, is it gonna go left, right, or I should really say up or down. So up or down, and then say, okay, if it's gonna go, whatever that value is, and just add it to this previous point. So in this case, it would be something like, oh, it would go like right here. So it's not gonna be extreme value. So kind of showing what this looks like. Note that this coding basically just to kind of make it a little bit more efficient. So we're basically going to start off with an average of 0. So it's going to start at 0 here, and the standard deviation of 10. So it's going to be for our white noise model. Okay, and then we're just going to put in this case about 175,000, right? Or sorry, 17,500. So about 20,000 points. And we're going to start off January 1st, 2015, like before. In this case, we're just doing our random model. So this is going to basically create our epsilon, our white noise. So if we stopped right here and plotted this point, we would just have a white noise model, right? But since we're going to do a random walk, we want to start off, in this case, we're going to start off at 0. So just like a simple 0. And what's going to happen is that every time, if I did this in a for loop, you can imagine y equals 0, and then the next one would be y1 equals y0 plus the first point of epsilon. And the next one would be y2 equals y1 plus epsilon. So just kind of going to show you what this would look like. It would be something like y1 equals y0 plus epsilon 0. Okay. And then the next one would be y2 equals y0, or sorry, y1 plus epsilon 1. If you look at this though, this actually means that, well, I could really have just done y2 is equal to what's y1. So I could have done this part right here. Let's paste it in. Well, y1 is just this. And so you can see it's like, oh, well, essentially, and then y3 turns out if I did all the math and pull this through, right? Y3 is equal to Y2 plus epsilon 2. Well, that's just saying Y0 plus, so this guy, plus epsilon 2. I was like, oh, well, we're just essentially just adding on a new epsilon each time. So since we know that, we already created our epsilon model right here, right? We can just do this cum sum, which is basically commutative sum. And what this does, basically, it will add up, it will make a point, let's say Y0, Y1, Y2, and it'll just add up the first point, the first 2 points, the first 3 points, and so on. So that way it makes it nice and easy, and we don't have to actually do a for loop. So this is actually a lot more efficient than, a lot more efficient than if we had tried doing a for loop like I kind of showed you a little bit. So this makes it nice and easy. I have my time series now, I'm gonna plot it out. And so we'll see now is that our white noise would have looked something like this. So if I actually plot out, let's go ahead and do this real quick. So I'm going to show you what the white noise would look like. Epsilon. Okay. So this is what a white noise looks like, which is really hard to see right now. But you can see basically just a bunch of randomness, right? So if I plot it out for about 20,000 points, it's basically a bunch of randomness. But since each one depends on the previous point, you can see it going up and up and up and up here, right? And note that basically it going up is because it's out of randomness. If I did this over a longer period of time, this probably would eventually start going down again, right? So it's kind of like every time you flip the coin, it lands on heads, you go up by 1. If you flip tails, you go down by 1. It's just I had a huge streak of going on heads, sometimes go down. And eventually, if I do this even a longer period of time, I'll go back down closer to 0 and so on. If I did this again, I might have equally gone down, up, and might have averaged over at 0. So know that just it ending at this high point is just random chance. Okay, so cool. Any questions on this random walk model then? Okay, cool. All right. So actually, you know what? I'll show you what. Let's try to run this one more time. Just see. And there it goes. You can see like it just randomly went down. And if I do this again, you can see in this case, this averaged out to 0. So again, randomness. Okay. So our next part is a little variation. This is a random walk, but with a drift. So the reason why it's called a random walk is kind of imagine it's usually compared to like a drunk person, like they can either go step left, step right kind of thing. Like they're generally like moving forward, but they're kind of go left and right. So eventually they might kind of keep going left and kind of go right just a little bit, kind of go back and forth randomly. A random walk with a drift is kind of like if someone, like I like to say, like if there's a little bit of a breeze or like the floor was tilted and the person tends to like every time they go left or right, but every time they step forward, they always step like off to the left a little bit. And so there's kind of like this general push kind of pushing them forward. So even though I have this random walk, which is what this is going on here, I'm just adding on a little extra part, which is the C. So it drifts with a particular value. So what's nice is that basically this average, it's going to basically have a drift towards C every single time. And all we have to do, which you can see this guy right here, this is just a random walk. So essentially all we can do is this cumulative sum of not just epsilon, but also just adding C to each value. So basically our random walk is going to have a little extra value every single time. And that will actually make our overall values drift forward. So if you look at this now, I plotted it out. I plotted out both the random walk and then the drift. So you can see the random walk, which is this one right here. But since C is being added up, like a little 0.1 is being added up every single time, you can see it generally going up like this. So this allows us to like basically have a little bit of emphasis on this part. And there are different models, obviously. You can think of different situations that would kind of be encouraged this way. One, for example, like if you're talking about stock market or something like that, you generally like the value of a stock or value of a house price, which is kind of like the project. That's going to be kind of like, what's it called? That would be like inflation, like, oh, like the values continue to go up regardless, or maybe it'd be something along like the market in general tends to go up. That would be that C factor is right here. Okay. Any questions on any of these three models? Random walk with a drift, random walk, or white noise? All right. So these are our basic models that are useful to kind of build everything else up from. So this leads us into our last part, which is autoregressive and moving average models. So let me go ahead and minimize this part. Cool. Restart. I don't know, Jupyter Notebook, I need to look into this. Jupyter Notebook's been taking a while for me to reset a lot of these things. But let's go into the autoregressive. I'll just wait for this stuff to clear out. So our autoregressive or AR models, kind of mentioned the curriculum. The idea here is basically, there we go, is that we have a formula here. And kind of breaking this down, we know epsilon t, well, that's just our white noise model. So we have some white noise, some randomness. And this is saying, oh, there's some value times the previous point. So it's very similar to like our random walk, but in this case, we actually can use the value, like not just saying, oh, it's dependent on the value, but there's some kind of method to it. So, or not method, some scaling to it. So note that if I just put 0 here, that simply is like the white noise with a mean of mu. So this mu part basically will keep it consistent, right? Which is white noise going around it each time. But if I have this value not 0, this phi value, basically less than 0 will be oscillation. And hopefully that kind of makes sense. Is that if I start off with a value, I'm just going to draw really quickly here. If I started off with a value like up here, and my it's going to depend on the next value. So my next value is like, what's my next value going over? So Google's going to take this value plus some extra, noise. Well, I'm going to take extra noise. So let's say it's like a value that goes up like by this much. Okay. Well, if this is negative, this is going to make the negative value of this. So I'm going to go up by this much, but I'm going to do a negative first. So I'm a negative of this, which is going to be here, going up. So it'll be like right here. And then so you can see the next part, like, well, this is negative. So the next negative value of this would be something like over here. And then let's go down by a certain amount. So it'd be like right here. And so you tend to see this kind of oscillation going forward, back and forth. And so the idea here is that if you have negative, it's going to basically be the inverse every single time, kind of hop around that origin, or sorry, the x-axis. And then if it's greater than here, basically kind of similar in the same like random walk. So you imagine like 1 was kind of an autocorrelation, basically. The value previously is going to affect it going upward. So that's just saying by how much does it go up by. Okay, does that make sense to people? Okay, so I think it's more clear when we kind of see a little bit of example of this. So if I run this, oops, there we go. Okay, so in this case, I'm just doing an average of 0, so it's easier for us to see. Standard deviation of 4, just 100 points. So let's see here. Okay, and this one I did a few different phi values. Let's try, for example, now let's just try 0 first, just to make it nice and clear. So you can see here, basically this is our white noise model, right? But if I get something like 0.1, you can see here, it's starting to move up a little bit, but not clearly, right? If I put to 0.5, we can start seeing that going forward. If I put a much larger value like 1.5, we'll see essentially it's going up and up for section of the best example. So let's do like 0.9 or 8. And you can kind of see it's going up a little bit. So there's still some white noise going on in here, but there's this general kind of like moving upward, right? So we're kind of like basically having, or not moving upward, there tends to be this dependence on the previous point. So for up here, we're likely to be close to this area, okay? If I had a negative point, like if I do, let's say, oops, I've done on my own keyboard today, negative like 0.3, you can see there's a little bit more fluctuation. If I put in a higher value, get some really strong fluctuation. You can start seeing it much more kind of going through. And I think if I get something really high, like 0.9, it'll be really obvious. And there you can see like it's basically fluctuating back and forth, back and forth, back and forth. Okay. And note that if I do something, I think if I can do like a negative 1.9, I think that might be high enough, is that this will actually make it go higher and higher as I fluctuate. So you can kind of see, it's a little hard to see, but it gets higher and higher and higher and higher. So let's see if I can do something a little bit smaller. There we go. So you can kind of see a little bit. The fluctuation is getting larger and larger and larger. Okay, so it's kind of a nice thing to kind of play around with. But does that make sense to everyone? Cool. And note, remember that this is basically a random walk, right? With when phi is equal to 1. So, okay. Cool. Anyone pronounce it differently, phi or phi? No. Okay.
I always heard phi.
Yeah, I always got like taught by a lot of like my physics professors. We'd use like this high, and they would pronounce it differently depending on their accents. So like I never knew exactly. Fun little story like Euler's number, E-U-L-E-R. I had one always pronounce it Euler, and so for the longest time I thought Euler was just like the right pronunciation, quote right, but like what everyone said. And it turned out like, oh no, that's like a very Italian thing for people to say. And I'm like, oh, did not know that. Like,
yeah,
so,
I always heard Euler too.
Yeah, so whatever, right? Pronunciations, it's that simple. The circle with the line through it, Greek letter. Okay, so our next part is our moving average model. So in this case, it's very similar, but in this case, it's a little different. So you'll notice that it's very similar, except this time we use theta instead of phi or phi, pho, whatever we call it. Epsilon t here. So the epsilon, remember, is our white noise. So instead of being dependent on the previous point, it's dependent on the previous noise. So it's not saying necessarily what is going to be the previous value. It's actually going to say, oh, what's it fluctuated from? So if we have theta equals 0, we get our white noise again. But if we get this theta greater than 0, we get auto-correlated with the past, but we're getting correlated with the past noise itself, which is a little bit, I think, a little subtle here. And then we can see there's going to be oscillation similar, but it's going to be less oscillation. So I think the best way to kind of show this is just go ahead and try it out. So if we run this guy right here, you can see a little bit of this fluctuation, and it looks like white noise, but you'll notice that like it's not quite right. Like it's a little bit different from white noise. And the idea here is that each point by itself is dependent by how much it fluctuated. So if I went down by this much, right, that means that epsilon t was this negative value. So it's going to take this negative value plus some noise. So it's going to say, okay, let me go off with this in this case, this negative value plus the mean, and that way goes 7. So like, you know, let's say -3 plus 7, so it'd be 4, and then plus some random value. In this case, it looks like it was another negative value here. So you can kind of see like how this kind of fluctuates based on the noise itself. It's a little hard for us to, in my head, it kind of, I'm like in my head, I can't really picture it without like graphing out. But if you have a higher dependence on the noise, you'll see a little bit more of this. And then if we get something like a high theta or high negative theta, that's low negative theta, we'll start seeing oscillation. For example, if I do really high, we can start seeing this. But you can see it's a lot less pronounced than it was in the autoregressive model. Okay, cool. So the main thing to note is that basically it's using the previous noise factor rather than the previous value itself. Okay, cool. So we can combine these together to get our ARMA model. So basically now we can say, oh, okay, we can look at basically our mu plus epsilon t, which is our white noise model, right? And then we basically have our autoregressive part, this theta, this phi t, y, and this theta epsilon t for our moving average. So autoregressive moving average, hey, ARMA, all right? So note, however, we only have to the previous point, but you could technically have functions that rely not just on the previous point, but maybe the other, like the day before yesterday, or the day before that, or the day before that. So that would be higher order. So what we can do instead, like for example, if we have an ARMA of 3,1, this means basically, oh, we have our value, basically, we have it dependent on 3 days prior to this, you know, but only 1 day prior for the moving average. Or you have something like this, where we have the previous day. I think in this case I might have not messed up. I might have wrote this out for people. Is that we can have essentially multiple parts in this case. I think I didn't finish this off, but you can see our factor of like, let's see here. This is not quite right. That's what's throwing me off. So you can have something like 2 factors here, and then plus that theta, what's it, epsilon? Epsilon t minus 1. So this is more correct, and I'll put epsilon underscore 1. Oops, no. There we go. So you can see here basically there's multiple factors in this case. There's going to be phi times this y t minus 2, phi 1 times y of t minus 1. So you would basically keep going through this part. So you can have it dependent on multiple things, not just the last previous day and stuff. So just kind of know that you can do that part. Okay, does that make sense? I kind of got thrown off a little bit by it because my equation wasn't quite right, but hopefully that makes sense to people, that you can basically use not just the previous day, but multiple previous days, or, you know, other days in the past. Cool. All right. So yeah, that's kind of all I have, kind of like a review part for this part. Most of it, to be quite honest, is a lot of the curriculum is, I think the labs themselves are good practice to go through, just to kind of like get a feel for how these parts go through, especially the diagnostic tools with those different parts. So, but I think once you kind of understand how these models kind of function, it's a little bit easier to understand like what they're trying to do and why higher order terms or higher order models will tend to do better, because you're basically putting in more features into it. Okay, cool. Any last questions then?